Hey guys, today we're going to be looking at the next section in your textbook, section 3.3. We're going to be in this section for a few days, and this is a really important concept as we move forward, and that is using the derivative to determine features about a function. So we're going to be looking at a series of problems where we're given either the graph of the function or a graph of the derivative, and we're going to have to make conclusions like, is this function increasing or decreasing? Is there minimums or maximums? Is the derivative increasing more here versus compared to this point? So on the AP test, there's a lot of questions where you're given a graph and you have to draw some conclusions about that graph. So that's what we're going to practice a lot in this video and on this assignment. In the next video, we're going to be doing it algebraically, where we're just going to be given a function and we're going to have to find the derivatives and find what are called the critical points, and then use those to find where a function is increasing and decreasing, where the mins and maxes are. And then eventually we'll also use the second derivative as well to make determinations about the shape of the function, things called concavity. So with that being said, let's go ahead and get started. Again, this will be a lot of problems on analyzing graphs. It's a very important tool that you know how to do this. So this assignment may take you a little while. Don't get frustrated if you miss something. Just take as much time as you need. And it's going to, again, train you to identify lots of features about graphs. So the first problem is going to start off pretty easy. We're given the graph of a function, and we're supposed to find where this function is greater than or equal to 0 on some closed interval. So if a function is greater than or equal to 0, basically what we're looking for is where is the function above the x-axis. And the fact that this actually includes an or equal to, we could actually say at or above the x-axis, right? So places where that's going to occur would be this little stretch here, and then this stretch from here to here. Couple things, remember when you're writing something in interval notation that if it includes that point, it should have a bracket. So on these endpoints, they're filled in, and that's why there's brackets on this. It says a closed interval. An open interval would mean that there'd be parentheses. All right, so we're supposed to find where the function is greater than or equal to 0. So for this problem, we're going to be just writing out this interval here, and it's going to be from -9 to -8. So we're going to use closed interval, -9 to -8. And then we use this union symbol to symbolize that there's another interval. And so that's going to be 5 up to 9. It's the x values. We're writing all x values. So 5 up to 9. All right. So that's the first type of problem. Another one that we're going to answer is determine all of the intervals in which the graph of the function is decreasing. So where is the function decreasing? In other words, what this is asking, f is decreasing, there's a few things we want to think about just in terms of derivatives. So what this means is that the slope is negative any place where f is decreasing. Slope is negative. Sorry, slope is negative. Which also implies that the derivative, right, because the slope of the tangent lines is derivatives. So as we move forward, think about these places where the function is decreasing. That means the slope of the tangent lines are negative, which also means that the derivative f prime of x is also less than 0. So just implications as we move forward. All right, so as far as this function, finding the places where it's decreasing, well, all the way from the beginning up to this point, it's increasing, right? So then it starts to decrease from here to here. Then it starts increasing again, and then it starts decreasing again from here all the way down to the end. These problems are can be a little bit tricky. Sometimes they get you with like these other little points sort of in between. Now, when you type this in, you do not want to include the endpoints. Do not include endpoints. Because at these endpoints right here, the function isn't decreasing. The slope of the function there, f prime of x, is actually 0 at that point. And that's actually going to be something we're going to call a critical value, a critical point here coming up. So it's actually 0 at that point. So it would be decreasing right after that point. So when we type this in, we're going to want to use a parenthesis. And that's going to be the x value from -1 up until +1. It is decreasing. Okay. And then we're going to do a union. Okay. And then it picks up again here at the x value of 5. Again, a parenthesis. Now we have to be a little bit careful because see how this sort of levels out right here? There's a point where it goes down and then it just briefly levels out and then it goes down again. So it's not decreasing on that whole interval because it actually sort of stops decreasing there for a moment at 7. So when we type this in, we're going to need to type it from 5 to 7 and then union 7 to 9. All with parentheses. If you miss one of these, it's generally because you used either the wrong parenthesis or bracket, or you missed one of these little points in the middle. So just be careful when you're typing these in. You should get 2 chances, so if you missed it, just go check all those little things. All right, so that's 2 of the types of problems. The next one, I want to do what are called relative extrema. All right, so in extrema, you see that word? We're going to be talking about that a lot. Extrema is basically a hill or a valley. In other words, the technical term would be a min or a max. Now there are 2 types of extrema. There are relative extrema, in this case a relative minimum, and there's absolute extrema. Relative are these little hills and valleys in the middle of the function, and an absolute extrema would be like the highest and the lowest values. We're just going to talk about relative for right now. So we're looking for a relative minimum. That's going to be a little, I guess I put these in the wrong order, huh? Sorry about that. This should be a max and this should be a min. Sorry about that. So relative minimum would be you're looking for little valleys. So if you see in this function here, there's a little valley there. So that is going to be a relative minimum. Notice what's happening here is the function is decreasing, right? So the slope is negative, and then at some point it switches there, and then the slope switches to increasing. So these relative minimums, you don't have to write this down for now necessarily, but when we actually do this algebraically, this will be very important. The derivative is switching from a negative derivative, a negative slope, to a positive slope. So that's how we're going to identify relative minimums. It switches from a negative to a positive slope. So that would be a relative minimum there. That's the only one. This down here would not be a relative minimum because it's not switching. It's just going down, 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 but it's not switching. So it's not a relative minimum. So there's only one place there. It says to type in the x value, so we're just going to type in 1. All right, let's go ahead and do another one of those. So that's asking for a minimum again. Would be the same spot for this one here. It switches from negative to positive. There would not be a relative minimum here because it's just going from negative to 0, then back to negative. So that would not be a relative minimum. Would not be. Here it goes from positive to 0 back to positive. So since it didn't switch in either of these places, there's no minimum there. A relative minimum or local, it uses in this case a local minimum. That's the same thing as relative. You'll see those used interchangeably. So a relative or local min, that occurs where it changes from a negative slope to positive slope. So that's where we're going to be looking for relative mins. Suppose you could write that down if you want to. So there's only the one spot here, and that is at x equals 5. Wanted to maybe see one where it asks us for a max. There we go. All right. So a relative or a local maximum on the interval. So local maxes occur just the opposite. So those are going to be the hills. So right here is a hill, right here is a hill. So notice in these that these hills, a relative max, that occurs when the slope changes from a positive slope to a negative slope. Changes from increasing to decreasing because we got a positive slope here and then it switches to a negative slope. So in the middle there, the slope actually hits 0. There's a horizontal tangent line there. So that tells us that's a relative or a local max. And same thing up here, it switches from an increasing function, a positive, to a negative. So that tells us that is a local maximum. So at those two places, the hills, if you will, are the places where there's local or relative maximums. So we're going to use the little plus symbol for this because we just want the x values, -4 and 3. All right, and again, we're going to be finding that algebraically in the coming videos as well. All right, the next one, we'll look at increasing versus decreasing. So this ties in along with the relative mins and maxes, because often we're looking at where a function switches from increasing to decreasing and vice versa to identify those relative mins and maxes. So on this one, we're supposed to determine all the intervals where the graph is increasing. So basically, where's the slope positive? So f is increasing. That means the slope is positive. And the implication in the future will be that the derivative is greater than 0, i.e. the derivative is positive. Okay, because if the slope is positive, the function's increasing, which also means the derivative is positive. So in this, we're just going to be looking for places where the derivative or the function is going up. So right there, it's increasing, and then it's going to be decreasing for a while, and then it starts again down here. Up to this point, it's increasing again. So the slope where the derivative is positive, which implies the function is increasing. We're again going to just use parentheses because at these points in -6, the slope is actually 0, right? And there's actually a horizontal tangent line there, which we'll do in the next one. Slope is 0. Same with here, 0 at those points. So we want the open intervals when we write those out. So we went from -6 to -4. And then a union. And then from, it looks like 2 up to 6. That. All right, and I guess we could do maybe one more of those. Maybe we'll get one where it's decreasing here. There we go. All right, so where's the function decreasing? So we're just going to be looking at the shape of the graph. Here starts out decreasing down to this point, then it goes up, and then it starts to decrease again, and then it goes up, and then it starts to decrease again. So we've got 3 intervals where it's decreasing. Those are all the times when the slope is negative. So if something is decreasing, slope is negative, which also implies that the derivative is less than 0, where the derivative is negative. So we're just going to write out these 3 intervals here, -9 to -5, union -3 to +1, union 5 to 9. All right, and there's one more type of problem on this one, and that is going to be finding the horizontal tangent lines. So let's go ahead and look at one of those. These can be just a bit tricky. First of all, let's think about what a horizontal tangent line implies. So a horizontal tangent line would mean a tangent line that would look like this, right? Horizontal, straight side to side. Okay, and let's think about what's happening here. So if it's a horizontal tangent line, this implies that the slope equals 0, right? In other words, the derivative equals 0. So where do these occur? Well, these horizontal tangent lines occur basically where a function changes from increasing to decreasing or decreasing to increasing. There is a few exceptions to that, which we'll talk about. But what you want to start by doing is identifying actually the mins and maxes. So there's a minimum down there where the function goes from negative to positive. And in between there, the function has to switch from negative to positive. It has to switch to 0 at some point, the slope does. So there's a horizontal tangent line right there. Okay. So there's another one up here at the top because it switches from an increasing function to a decreasing. There's got to be a horizontal tangent line. Down here at this minimum down here, there would be a horizontal tangent line. It's from negative to positive. And then up here, there's going to be another one because it switches from positive to negative, right? So there's 4 places where there's horizontal tangent lines. Now, in addition, there is some places, and they like to throw these in here, both on Delta Math and on the AP test. There's some places in here like this one here. See how it's increasing? And then it just sort of levels off, and it is 0, and then it starts increasing again. So there's no min or max there, but there is a horizontal tangent line there because the slope at that point is 0. So you really got to look for these little places, and they like to sneak them in there where it sort of just levels off. So here's decreasing, it switches to 0, and then it decreases some more. There is a horizontal tangent line right there. So there's 2 additional spots. These are all critical points, but these 2 are actually called inflection points, which we'll talk about in the coming weeks. The blue ones are the more important ones, but the red ones, for the sake of the graph, we need to also identify those as horizontal tangent lines as well. So we're going to type all of these in, the x values. There's going to be a lot of them. I think we have 6. So it's going to be at -7, at -4, at -1, +1, 3, and 5. Let's look at one more of those. So another place we're trying to identify all of the horizontal tangent lines. So there's the curve of the mins and maxes, right? Here and here, there's a max. But we also got to look at the other little points where it levels off. So that's going to be right here. There's a horizontal tangent line. And right here is a horizontal tangent line. There was actually a problem similar to this on your semester review where we had to find the horizontal tangent lines. So it is definitely an AP type problem. All right, so we've got just 4 points on this one. Go ahead and type those in. We're at x equals -5, x equals 0, x equals 2, and x equals 5. All right, so I've showed you the 4 types of problems that are on this particular section. Again, intervals of increasing and decreasing, whether the function in general is positive or negative. So just identifying if the function is above the axis or below the axis. The extrema are going to be the mins and maxes, and the horizontal tangent lines occur at these places where it sort of levels out where there's a min or a max